usual, up here for the syllabus, project 4 is due today. It's on green paper, the one with the student ID number. Put that in your folder before you leave. If it's not done, remember you can hand it in up to a week late, 10% penalty. So I will take it up until May 4th. And next class, Wednesday, I'll be assigning take-home quiz 6 that will be due Friday. And then next week, we'll review for the test 3 and take test 3. All right, so let's go through the preview exercises and the demo together. All right, so we have the size of an initial rabbit colony, so meaning the size when time is 0, t in years, settled on planet Rabbit Utopia was 1,000 rabbits. Okay. So if the rabbit population increases by 1,000 rabbits every year, we want to find a function, p of t, that models this population growth. All right, so we started with 1,000 rabbits and we grow by 1,000 every year. So the next year we have 2,000. The year after that we have 3,000. And then we have 4,000, 5,000, 6,000, right? Growing by 1,000 rabbits every year. When your growth rate is constant, you're growing by a constant amount every year, what kind of function is that? A line, great. So an equation for this line would be my y-intercept, or my initial amount, 1,000, plus 1,000 t. Start with 1,000, grow by 1,000 every year for t years. And that is linear. Now, to contrast, instead of adding 1,000 every year, I'm going to double the population size every year. Okay, so the rabbit population is actually going to double. So it goes from 1,000 to 2,000. So far it looks the same as the linear growth. But in year 2, how many rabbits am I going to have? 4,000. So I have now gotten bigger than the linear growth. And then I would have 8,000, and then 16,000, and then 32,000. So you can see very quickly, this kind of growth with doubling is going to outpace the linear growth with the adding 1,000 every year. All right, so then I'm just going to do something a little bit fancy. I'm going to rewrite each of my population sizes using a times 2 to the something. So 1,000 is, you could rewrite as 1,000 times 2 to the 0, because anything to the 0 is just 1. 1,000 times 1 is 1,000. 2,000 I could rewrite as 1,000 times 2 to the first, because that would be 1,000 times 2, which is 2,000. And then 4,000 I could rewrite as 1,000 times 2 squared, because you do the exponent first. 2 squared is 4, times 1,000 is 4,000. 8,000, that's 1,000 times 2 cubed. 2 cubed is 8, times 1,000 is 8,000. This one would be 1,000 times 2 to the 4th, 1,000 times 2 to the 5th. So based on that third row there, could you write a formula for how to get the population in year t? 1,000 times 2 to the t. So you're starting with 1,000 rabbits, you're doubling every year for t years, and repeated multiplication times 2 you write using an exponent. So to the t, 2 to the t. And what kind of function is this? Exponential, that's what we learned last class. When you increase by a constant multiplicative factor, right, as opposed to a constant amount, it's exponential growth. Okay, so now I have functions for populations in 3 different cities, A, B, and C. T is in years again. Which of these cities have populations that are changing exponentially? B and C, right? Because they have variables in the exponent. That's what makes it an exponential function. All right, what is the initial population of city A? 300. If you make T 0, that's how you get your initial population. And city B, initial population? 270. City C, 600. Good. All right, city A's population, how is it changing? increasing, what is that constant rate? 1.3, is this all measured in thousands? Yeah, 1.3 thousand each year. So it is increasing by 1.3 thousand, that would be 1,300 people every year. Population B, how is it increasing? By 2.1% each year, right? So the 1 in the 1.021 indicates you get to keep 100% of who was there, right? And then the 0.021, convert that to a percentage by moving the decimal 2 to the right, and that represents an additional 2.1%. So this city B is increasing. We know it's increasing because it's keeping 100% of what it had, and then it has an additional 2.1%, increasing by 2.1% each year. Okay. And then city C, what's happening to city C's population? It's definitely decreasing because my multiplication factor, my factor is less than 1, right? If you multiply 600 by a number smaller than 1, you're going to have fewer than 600 people, right? So this means I'm starting with 600 people, and 97.8% of them are staying in town C, right? So what percentage is leaving then? 2.2%, yeah. So 2.2% is leaving. So city C's population is decreasing by 2.2% each year. So be careful not to write decreasing and a negative sign. It's like using a double negative when you're speaking. If you write the word decreasing, you leave off the negative sign. If you wanted to use a negative sign, you would say changing by negative 2.2% each year. Any questions there? All right, let's look at today's demo. So I want to figure out how to identify a linear function versus an exponential function if you're looking at a data table. So the table below represents values from one of these functions, f and g. One of them is linear, one of them is exponential. Can you identify which is which? Yeah, so first thing to check is is the change in x constant? 20, 25, 30, 35, 40, 45, those are all changing by 5, yeah. So you got to check that first, because if they're changing by random amounts, it's harder to see whether it's linear or exponential. But yes, the change in x is always 5 in this example. Okay, so what can you tell me about consecutive differences of f of x? 30, 40, 50, 60, what are they changing by? 10. So my change in y for f of x is 10, right? Constant, always 10. All right, what if I look at differences for g of x? Yeah, let's actually get the calculator out because these are some uglier numbers, and I think actually there's a typo in here, so let me just double check here. Nope. Yeah, okay, so I threw in an extra number there. Should be 1690, and then this should be 2197. So sorry, yeah, there's a typo in here. This is 2856.1 and 3712.93. Okay. So I was just fixing a typo there. The first three are fine, yeah. All right, so if I subtract, if I look at the difference between each set of numbers, 1300 minus 1000, the difference is 300, right? 1690 minus 1300 is 390. So I'm just looking at the difference between the successive numbers. 2197 minus 1690, and I get 507. 2856.1 minus 2197, 659.1, and one more, 3712.93 minus 856.83. Okay, so are those differences constant? Are they always the same? No. So it's definitely not linear, right? They told us one was linear and one was exponential, so this one has to be exponential. Another thing you might notice about these is that 300, 390, 507, these differences are getting bigger, right? They're not just not the same, but they're increasing. So that would indicate that this is exponential growth. So they are not constant. So that means f has to be linear, g has to be exponential. All right, so a little summary of linear versus exponential growth. The rabbits, 1000 plus 1000t, the growth of a linear function is additive. You're always adding some amount for every unit of time, right? For this example, we added 1000 rabbits every year. And then the growth of an exponential function is multiplicative. Every year you multiply by something, right? So that means for the rabbits, every year that passed, we multiplied the number of rabbits by 2. So linear, additive, exponential, multiplicative. And in general, for a linear function, your output is always some initial quantity plus your rate of growth, which is your slope, times your input. And for exponentials, your output is your initial quantity times a growth or decay factor raised to the input. Okay. So in conclusion, we say that linear functions represent quantities to which a certain amount is added or subtracted for each unit of time. And exponential functions are quantities that are multiplied by a constant factor for each unit of time. All right, so you have enough to get started on your own.